Hey! Today we are solving rank transform of an array. We take a list of numbers and replace each one with its rank, meaning how big it is compared to the others. To do it, we will use just three tools: sorting, a set, and a hash map. That is it, so let's meet those tools first. First tool, the list, also called an array. Think of a hallway of numbered lockers. Locker 0 holds 40, locker 1 holds 10, and so on. An array is just an ordered collection where every value has a position. In short, a list is a row of boxes you can look into by number. Second tool, the set. Imagine a guest list at a party. If someone tries to sign in twice, the list still only shows their name once. A set is exactly that, a collection that automatically throws away duplicates. In short, a set keeps only the unique values. Third tool, the hash map, called a dictionary in Python. It is like the contact list on your phone. You know the name, you instantly get the number, and you never scroll through every contact. A hash map stores key-value pairs so lookup is instant. In short, a hash map lets you ask a question and get the answer immediately. So what exactly are we asked to do? Every number gets replaced by its rank. The smallest number gets rank 1, the next smallest gets rank 2, and so on. If two numbers are equal, they must share the exact same rank, and there are no gaps between ranks. Let's walk through a tiny example next. Take 40, 10, 20, 30. 10 is the smallest, so it gets rank 1. 20 is next, rank 2. 30 gets rank 3, and 40, the biggest, gets rank 4. Now we write those ranks back in the original positions, so the answer is 4, 1, 2, 3. Notice the output keeps the original order of the array, only the values change. Here is the twist that trips people up. If the array is 100, 100, 100, all three are equal, so they all share rank 1. The output is 1, 1, 1, not 1, 2, 3. This is exactly why we need that set from earlier: duplicates should not use up extra ranks. So here is the trick. If I line everyone up from shortest to tallest, each person's position in that line is their rank. Same with numbers, sort the unique values, and the position of each value in the sorted list, counting from 1, is exactly its rank. Then we store value maps to rank in a hash map, so we can look up any number's rank instantly. In short, sort once to learn the ranks, then look them up. You might wonder, why not just sort the array itself? Because the answer has to line up with the original positions. 40 was first in the input, so rank 4 has to be first in the output. If we sorted the input in place, we would lose track of where everything came from. So we sort a copy off to the side, learn the ranks from it, and leave the original untouched. Let's write it. First, set of ARR throws away duplicates, because equal values must share one rank. Then sorted lines up those unique values from smallest to largest. Now enumerate walks through them handing out positions starting at 0, so we add 1, because ranks start at 1. After this loop, the hash map says things like 10 maps to rank 1, 20 maps to rank 2. In short, this block builds our instant lookup phone book of ranks. Second half. We walk the original array in its original order, and for each value we just ask the hash map, what is your rank? That lookup is instant, no searching. We collect the answers into a new list and return it. Notice why this works for duplicates: both copies of 12 ask the same phone book, so both get the same rank. And here is the exact same logic squeezed into a few lines using comprehensions, which are just compact loops. The first line builds the value to rank map, the second line looks up every value. Nothing new is happening here, it is just the Python way of writing the two loops we already understand. One alternative: keep the sorted unique list, but skip building the hash map. For each value, do a binary search, which means repeatedly cutting the sorted list in half to find where the value sits, and that position is the rank. The plus point is you skip storing the extra map. The minus is every single lookup now costs a small search instead of being instant, and the code is a bit fiddlier to get right. Time-wise, both approaches cost big O of n log n, because sorting dominates everything else. Space-wise, the hash map version uses big O of n extra memory for the map, and honestly the binary search version still needs the sorted list, so the savings are tiny. When would you pick which? Almost always pick the hash map version, same speed, simpler code. Binary search only wins if memory is extremely tight. Let's stress test it. An empty array. The set is empty, the map is empty, the loops run 0 times, and we return an empty list, no crash. All duplicates. The set collapses them to one value with rank 1, exactly what example 2 wants. Negative numbers. Sorting already knows -9 is less than 0, so no special handling needed. In short, the clean solution survives every edge case for free. Quick recap. Throw the values in a set to drop duplicates, sort them so each position tells you the rank, store value to rank in a hash map, then walk the original array replacing each value with its rank. Total cost, big O of n log n from the sort. That sort, then map, then lookup pattern shows up all over coding interviews, so keep it in your back pocket. Thanks for watching.